So, now we will actually look into how to differentiate between probability of call loss and probability of switch being in blocked state. These are two different things, and the ways of actually estimating these two in the switches. So, if there is a switch and there is a call which arrives, and when the call arrives it finds that switch is in the blocked state. Now, call will not be able to go through. So, the probability that your call will not go through is known as call loss, because call has been lost. So, if you make 1,000,000 calls, out of which 10,000 calls you found that switch was in blocked state at that point of time, call cannot go through. So, that is a call loss, or we call it a call congestion. Okay. Secondly, even if the call comes or call does not come, does not matter. You look whether switch is in which state. If switch is in the blocked state, even if call does not come, it does not matter. If there is no call coming and switch is in blocked state, there is no loss. There is no call is being lost actually in that case. So, the second possibility is we call it that switch is in the blocked state. So, that we call as a time congestion. So, now question is how these two are going to be related. One thing which is sure, that when switch is in the blocked state, that is basically fraction of, you are actually technically observing the time. When, for example, I estimated in my previous lecture probability of switch being in blocked state. What does that mean? You observe the switch for a long time, say a few years, and you find out fraction of time for which switch was in that state, which is the blocked state. So, ratio of that particular time divided by the total observed time will give you the time congestion. That is why the time congestion word is being used, but the probability that your switch is in blocked state does not mean call is blocked. Only when the call will arrive, then only the blocking will happen for the calls. So, call congestion usually will be lower value, having a lower value than the time congestion. So, that I think intuitively is clear, but let us build up a relationship between these two. So, if we define that probability that of call arrival is defined as PA, probability that a call is arriving, and I also define PNA. This is the conditional probability that a call arrives when switch was in blocked state. Okay. So, I define call congestion as probability of call loss PL. I define the time congestion as PB, being in the blocked state. So, now I actually have 4 variables and these need to be related to each other. Remember, this is a conditional probability when switch was in a blocked state and a call arrives. So, this call is going to be lost, and when a probability that a call arrives, this is the probability that the call will be lost, okay, conditioned on that call arrives actually. So, P into L into PA, this gives the number of calls which will be getting lost over time, okay. Remember, when I am saying when a call arrives and it finds switch is in blocking state, that is a conditional probability, that is a call congestion, and this will be on an average a number of calls lost over long time. If my arrival rate is high, more number of calls will be lost. Arrival rate is lower, less will be lost over time, okay. So, this should be equal to, because both are going to lead to the same thing, this will lead to nothing but probability that is a conditional probability that call will arrive when switch is in blocked state, and probability that you will be in blocked state is PB. This technically is a Bayes rule. Okay, what I am saying is that there are event A and B, switch is in blocked state and calls arrive. So this PAB, that both things happen, is PA given B. So probability that switch is in blocked state, probability that call arrives conditioned on switch is in blocked state. Okay, so this represents right side. It is also possible to write P of B conditioned on A, the call arrives, and when the call is arriving on that condition, that switch was in blocked state at that point of time. This is a technically Bayes rule which I have written here, and this is what I am going to use to estimate the relationship between PL and PB. So I can now write, and we will do it for M by N composite switch only. I can write now PL as and of course now very important observation which you can make, probability of call loss and probability of blocking will be almost same if my call arrivals probabilities are independent of switch state. If they are independent of switch state, this and this has to be exactly same and they will cancel. Both of them will be call loss probability or call congestion and time congestion will be same. Okay. But that actually does not happen. This is going to be a true statement if my N is comparatively much smaller than M. M is very large. So the arrival probabilities does not get impacted by the change in switch state. They will be almost same and both of them will be similar. But when M and N are not, N is not much smaller, not much smaller than M, then this is PL is equal to PB cannot be taken. We have to actually estimate a relationship between that. So what is Pn of A? Let me see how we can find out. So when the switch is in state A, then what is the arrival rate? I have to find out that, and a small elemental time delta t. So I can put some delta t here. So that is the probability of arrival when you are in state n in small time delta t. Probability of arrival, this will be the average value of the arrival rate. With every state change, there is going to be different arrival rate. Remember in the previous lecture, when you were in state 0, arrival rate was m lambda. When you were in state 1, it was m minus 1 lambda, and so on. I make an estimate, average estimate, depending on the probability of the events, and I will get this average value in totality. So that is what is going to be the call arrival rate on an average basis, which is independent of state. States actually have been ironed out by taking what we call a probabilistic average. So in this case, lambda t now can be estimated as, because I am taking a probabilistic average, I can write that I am in probability of being in state k, and state k, what is the probability of, what is the arrival rate. So I am taking a probabilistic average, and my all states goes from k to n. So that will be PA. So I can now solve it. So I have already, remember I am taking ratio delta t's will cancel, these are immaterial. So P of L will be lambda n divided by summation of, I have to write down this thing, Okay. So, this what will be the relation. Now, lambda t, the arrival rate, and lambda n, they will be related. Lambda n will always be smaller than lambda t. Okay. This of course you can make a drawing. So, when you were in state 0, m lambda was the arrival rate. As you keep on moving the state, it becomes m minus 1 lambda, and you will keep on reducing. At this point it will be m minus n lambda, and this monotonically decreasing as your states, as you are actually going to from 0 to nth state. So, the average value will be somewhere here, and this is the smallest value. So, this top one is the smallest value. So, this has to be smaller than the average, and of course, with this you can figure out that this is going to be smaller than this. So, PL is always going to be less than PB. This was also the intuitively the result which I explained in the beginning. The call loss probability will be smaller than the switch being in the blocked state, that probability. Okay, it will be smaller than that. So, let us solve it. So, lambda n essentially will be m minus n. So, I am just going to put everything in this expression and we will solve it. And this expression will be that is your lambda k. Probability that you are in that state, I am going to use that Angset probability distribution, will be given by MC k lambda by mu raised power k divided by, again there has to be a summation, okay. So, I can also now replace this PB, the blocking probability, by in fact I have to put again now this is independent of k, this and these two are same, so I can cancel them actually. Once I cancel, I will get, I can actually erase it now from here. Okay. So, this lambda will cancel with this one, this m factorial by n factorial m minus n m factorial by k factorial so I can cancel and I can make it minus 1. So, and I can make m here and take one m here out. I can do the similar exercise here, this m will cancel and I will have m minus 1 Cn lambda by mu raised to power n, summation of k goes from 0 to n, m minus 1 C k and of course you can see this is the same expression as the probability of being in blocked state for m by n composite switch, except now instead of m I am going to have m minus 1 here. So, I can write this thing as nothing but probability of blocking, but for m minus 1 inputs. Instead of using m by n, if I use m minus 1 by n composite switch, the probability of it being in blocked state is equal to probability of call loss for a m by n switch. So, which actually implies that P L of m should be equal to P B of m minus 1. That is how your call congestion and time congestions will be related to each other.